Okay, we'll start from current slide. Okay. Just a little refresher. Let me take back. Last thing we were working on. First, any questions on anything we've done so far? Okay. Yeah.
You said, well, what? You want to have what?
Any questions? Anything we've done so far? Okay. The last thing we were working on was how to set up these trigonometric substitutions. And what you look for are these forms. My ears are popping, sorry. Square root of a squared minus u squared, square root of a squared plus u squared, or square root of u squared minus a squared. Those are the three forms, and this is done with sines, this is done with tangents, that's done with secants, substitution. All right, so let's go here and see what we have here. They jump right into a fairly complex one. Okay, but it's not too bad. Famous last words. Let's see what we can do. What would be your guess of how we would proceed on this one? What's the most complicated, messiest thing to have to resolve here? The radical in the denominator. Okay? Well, there's the radical, and it's a 9 minus x squared. Any suggestions for what we might use as our trig substitution? Well, understanding that they are. Oh, man, I didn't know they gave it to you. What would you use? Go ahead. Second? Okay, you could use cosine, but most of the time we use sine. Sine and cosine are pretty much interchangeable. There it is, right up there, you see? All right, except they use a sine theta. This doesn't have a theta in it. So let's see what we would use. Let me get my pen set up. Okay. So what we'll do, our trig substitution will be let u is what we usually use for a substitution, right? Okay, now what would we want to use for a? Any ideas? Any ideas? Here's the hint. Except not 9. That's squared 3. 3, because that'll be a 3 squared, so that'll be 3. Let u equal 3 sine, or you could do cosine, and then your theta, instead of theta, this is an what we got here? Not theta, but it's right there. X. Okay, good. I feel like a dentist here pulling teeth. Okay, now, only I said this backwards. Sorry. Sorry. Let me go back and clean up this. Remember, with the trig substitution, you go the other way. Okay? It's let u, not u, let x, that's where we put the x, equal 3 sine, and here I would use theta. I wouldn't use u, I would use theta. Let's let x be the length thing, and that would be your u. A is the 3, just like before, and then sine theta. All right? Now, we can see from here, that's going to be our x. Now, we don't really have a plain old x over here. We have two different ways of expressing x, kind of. What are those two ways? It's the first thing you see. dx. Okay? If x equals 3 sine theta, then dx is equal to what? I'll have to talk to your Cal 2 instructor, I think. No, dx is equal to, what you did here was take the derivative of x. What you do over here is take the derivative of that. What's the derivative of 3 sine theta? 3 cosine theta. With one other little thing. It's a differential form. Anytime you have a d over here, you got to have a d theta. Perfect, perfect. Okay, so that takes care of one of the x forms there, kind of. It's a dx, so we got that. What's the other x form you have there in the integral? It's not x, but x squared. So if x is equal to 3 sine theta, then x squared is equal to what? Help. Say again? A little louder. Okay, you squared the x, so square what's over here? What would give you? 9. Say again? Sine squared theta. Perfect. Okay. So now, let's take one more step here. So while we're there, let's do the radical. Okay? So this also implies that the square root of 9 minus x squared would be 9 minus, and x squared is 9 sine squared theta, right? Agreed? Or not? Got it? Okay, agreed. All right, what can you do with that then? Anything? Anything? Anybody have any ideas? How about factoring out a 9? Would that be okay? So it would be the square root of 9 times what's left? 1 minus sine squared theta. Okay, is this beginning to look like something we can deal with now? What's the square root of 9? 3. What is 1 minus sine squared theta? Cosine squared theta. And what's the square root of cosine squared theta? Cosine theta. Whoa! Look at that. Okay? So now let's take our integral. And the dx was this right here. 3 cosine theta d theta. Agreed? Yay or nay? Okay. The x squared down here is 9 sine squared theta. Agreed? And then your radical, 9 minus this, is just simply 3 cosine theta. Agreed? Got it? How's that radical there? It's that one. We just plugged in the x squared, and that came out 3 cosine theta. So we put that in instead of the radical. So there's your dx, there's your x squared, and there's your radical. Ha! I see something that can go right now, don't you? What was that? The 3 cosine theta. divides out, numerator and denominator. Okay, we still got a little ways to go now. So what we have is the integral of d theta over 9 sine squared theta. One thing I'm going to do with that is pull out the 9. So that's going to be 1/9 the integral of d theta over sine squared theta. Okay, now, that's problematic, isn't it? Do you remember our power reducing formulas that we did last chapter? We had a sine squared, how we can diminish that power. Oh, wait. No, that won't work either. Thought maybe a substitution would be good, so I don't think that'll work. Okay? Glance back in your text. I said last chapter, last section. Trigonometric integrals. Remember when we talked about power reducing formulas? Do you see on page 532 that little gray box in the middle of the page? Now, some of you don't have books. In fact, none of you have books, do you? Uh-oh. Okay. I will have to relate it to you then. Got it. Okay. So I'm going to write this down. What you just said, sine squared theta is equal to 1 minus cosine 2 theta. Running out of room here. Divided by 2. All right. So this will then make it, you got a 2 in the denominator. We'll worry about that in a minute. So this will be 1/9 times the integral. D theta I'm going to put here. And the 1 over sine squared, that was going to flip this over, so that's going to be a 2 over 1 minus cosine 2 theta, which is not particularly pretty. In fact, that may not be the way to go on this. In fact, I don't think it is the way to go on this. Okay. Sorry. It's not the way to go on this. I forgot something. Well, I think I wanted to leave something there. I thought of this at first and then dismissed it until just now I remembered. Yuck. Let's rewrite this as, I am going to pull the 1/9 out. What we have here is a derivative of d theta. Oh, wait. That's not where I want it. Y'all should have picked me up on this. 1 over sine squared is the same as, anyone remember? 1 over sine squared, reciprocal identities in trig. Gonna have to talk with your trig instructor. Cosecant. So this will be cosecant squared theta d theta. Right? I pulled the 1/9 out front. Here's what. I glanced at it, thought of it, and dismissed it. I shouldn't have. Does anyone recall what the antiderivative of cosecant squared is? Second? Not 1 minus. It is, the antiderivative is minus cotangent. Okay. You're right, or you're good thinking. The Pythagorean identity for cosecant squared is cotangent squared plus 1. But that's not what we're looking for here. We said the antiderivative for cosecant. Derivative of cotangent is minus cosecant squared. Remember, derivative of tangent is secant squared. Derivative of cotangent is minus cosecant squared. So this then gives us a minus 1/9 cotangent theta. It's one other little thing. Indefinite integral. Indefinite integral. Plus C. That's yes in Spanish. Okay, C, yes. Okay, there it is.
It's just cotangent.
No. Derivative of cotangent is cosecant squared. Derivative of tangent is secant squared. You don't have your books. I was going to say look in the book and look it up. But remember your derivatives. Derivative of sine is cosine. I'm not writing the theta, that's going to be derivative of cosine is minus sine. Derivative of tangent is secant squared. So derivative of cotangent is minus cosecant squared theta. And then derivative of secant is strange secant theta tangent theta. So the derivative of cosecant is minus cosecant theta cotangent theta. This is the one we're doing. If the derivative of cotangent is secant squared, the antiderivative of cosecant squared is cotangent, going the other way. And that's why it comes like this, but it's a minus there. Okay. Now, all right. But, so can I erase all those at the bottom? That was just refresher course. Trig students, okay? So I'm going to erase these if I can get the eraser to activate here, because I need the room down here. That was memory, going back and remember things. All right. We still aren't quite where we need to be. And here's why. Because our problem started with x's, we made up the theta part. Okay? We need to get back to x's. Right? Now, you can do it sort of by remembering a lot of different trig identities, which could be sort of painful, it sounds like, but you did remember some. But the easier way to do this is go back to our very first little let x equal. Okay? If x is equal to 3 sine theta. Now what I suggest is dividing both sides by 3. That wipes you out there, and then you get that sine theta is equal to x over 3. Now someone remind me what the definition for a sine is. Remember some old hen, or hag, or Sakatoa, or any of those things? You were not in my class, but these other two should. Okay, what is it? Absolutely. So let's draw us a little right triangle down here. It doesn't have to be very correct or anything else, just needs to be a right angle. Okay, that makes this, why don't we let this be our theta, right? And the opposite is x, and the hypotenuse is 3. Right? That would represent sine theta being x over 3, right? Now, what we want is what in the world is cotangent theta? Anyone remember what cotangent theta is? Okay, how about tangent theta? In terms of old hens. And say again? Is what? Opposite over adjacent. That's what tangent is. So guess what cotangent is? Adjacent over opposite. We've got to figure out what that adjacent side is. Is there any way to do that? This is good old Pythagorean theorem, right? What does it tell you it is? Anybody? This is even prior to trig. What's it? Okay. Now, we're going to come back and change this again in a minute. Let's call this A, B, and C. What's Pythagorean theorem in terms of either, or anything in terms of A, B, and C, and specifically we want it in terms of B. What would that be? A little louder?
A squared plus B squared.
Absolutely. A squared plus B squared equals C squared. Okay, we're interested in B, so let's plug in what our others are. So A is x, so this will be x squared plus, and we don't know what B is, that's what we're looking for. B squared is equal to C is 3, so that would be 3 squared is 9. So the B squared is equal to what? 9 minus x squared, right? And then we want B, so what would it be? How do you the square root of 9 minus x squared. And looky here, folks. There it is right there. Square root of 9 minus x squared. It's right there, kind of in front of us. Okay? So, we just said that cotangent theta was adjacent side, which is B, which is the square root of 9 minus x squared, over the opposite side, which is x. All right. Now, can I go on and erase some of my scratch work here? That really is important, but I didn't place it very well, so I'm going to have to lose it for now. I'll draw it again if you need it. Okay? Hopefully you are wiser in your use of space on your page. So what do we have here now? We have this as minus 1/9, okay, times the square root of 9 minus x squared over x plus c. So we could write that as the square root, or minus the square root of 9 minus x squared over 9x plus c. That's no better or no worse than the other, but it's a little more concise. Let's see what they got. Minus the square root of 9 minus x squared over 9x plus c. Yes, they got it right. Good for them. It's kind of nasty out there, isn't it? Yep. All right. See how that works? Thing did skip or missed over was that cosecant squared is a perfect derivative. So that made the problem fairly easy. All right, to erase this, and we'll see how they did it. Was there a question? Okay. All right. So let's erase that, and let's see what they did. First, note that the basic integration rules do not apply. Hey, we can't do a substitution. We can't do anything to clean up that mess. It's a mess. Now, if that was a 2x dx in the numerator, yeah, we could do something with that substitution. It's not. It's just a dx. So, usual integration rules, power rules, that kind of stuff, not going to help us here. But it is, the radical in there is of one of those forms that is square root of a squared minus u squared, where a is 3 and u is x. Okay? With that in mind, then, we do a trig substitution. But when you're doing your substitution this way, rather than coming up with a new variable u, which I started to do, and doing in terms of what we got, we're going to let the new variable be the x, the very thing that was our primary variable here. And we'll say let x equal the a, which was 3, times the sine of theta, 3 sine theta. Okay? That's going to be our substitution. Now, we take a look at this, and we need to account for every form that we have of x up there. Okay, we have x squared and we have a dx. So at some point or another, we say dx is equal to, since we know what x is, that's the 3 sine theta, okay, then the derivative of that would be 3 times the cosine of theta d theta. Now the reason we didn't, or I didn't want to use the cosine, is the derivative of cosine is minus sign. There's another minus sign for me to keep up with. So it's easier to use the sign substitution. Okay? Then the next thing we needed was what? I did the x squared. They went straight to the square root of 9 minus x squared is 3 cosine theta. Now, I don't look at that and see it and say, oh yeah, that's true. But I do see if I put in x equal 3 sine theta, x squared is 9 sine squared theta. Factor out the 9, that gives us the 3 when you take the square root of it. And then you have a 1 minus sine squared theta. That's going to be cosine theta. Yes, or cosine squared theta, and then take the square root of that, you get cosine theta. Okay? Now, frankly, to me, that was the first one, the better one to do first, than do the second. All right, and then they go on and draw the triangle, which I drew later. They drew it now, and say from this right here, no, where is it? They didn't write it down here. It was on the previous slide. X equal 3 sine theta. So then divide both sides by 3, and you get sine theta is x over 3. So if this is your theta, opposite over hypotenuse, x over 3. Then, because we do need to know what cosine theta, or cotangent theta is, now it's not obvious. Where did cotangent come from? Only later do we need to know that. So they threw this in way too early here, but we will need it, and cotangent theta will be adjacent over opposite. Well, the adjacent from Pythagorean theorem is 3 squared minus x squared, would be b squared, and b is the square root of that. Okay. That was way premature here, okay? But we will need it. All right, so now we rewrite this in terms of theta. The dx is 3 cosine theta d theta from here, okay? The x squared is 9 sine squared theta, and then the square root of 9 minus x squared is 3 cosine theta, just like we did, and then you see those go out. So that would be 1/9 the integral of d theta over sine squared theta. Now, what I didn't focus in on, and I should have, was that 1 over sine squared is cosecant squared, so that's the integral, 1/9 times the integral of cosecant squared theta d theta, and that is a perfect antiderivative of minus cotangent. So that gives us minus 1/9 cotangent theta plus c, because it's an indefinite integral. But, see, they had already done this for us, that the cotangent theta is adjacent over opposite is the square root of 9 minus x squared over x. Plug that in here, and that gives us minus 1/9 of that, so that would be minus the square root of 9 minus x squared over 9x plus c. Make sense? All right. To sort of keep your insight hat on. All right. And here's that's the top part of the alphabet's doing pretty well now. The bottom part, kind of shaky there. Only one here. Okay. Note that the triangle and figure 8-6 can be used to convert thetas back to x's. That's exactly what they did. They showed it, now they tell you how. Kind of backwards. We're finishing up example 1 on page 542 if you have your text. Okay. Now, there's a little blurb at the bottom of the page in technology using computer algebra system. I don't have that. If you have it somewhere on a fancy calculator or something, by all means use it. Okay, but I don't. Oh. Now we're backing up, telling us how they got that. A little late now, but that is how we got it. All right. They are skipping example 2, example 3, example 4, and jumping back straight to theorem 8.2. So let's us go in there and do example 2, 3, and 4. Okay? All right. Any questions so far? Excuse me. All right, here's what we got to find next. The integral of dx over the square root of 4x squared plus 1. All right. Any suggestion on what we do? Any? You got a little bit of a problem here, and this isn't quite fit your form perfectly. Your form is usually, the one with the plus in it would be the square root of u squared plus a squared. Well, if you were using that form under the square root, what would the u be here? If that thing is u squared, what would u have to be? Anybody? This thing right here, 4x squared was u squared. What would your u have to be? Say again? Okay, here's what I'm saying. Our model here is the square root. The one with a plus in it is u squared plus a squared. It can be written a squared plus u squared. That's the model. Now, the a is a constant. That's going to be 1. So I'll just immediately say a is equal to 1. Okay. But what would your u squared be then? If u squared is equal to 4x squared, what would u be? What would you be? No. 2x, exactly. 2x, because when you square it, you get 4x squared. All right, so let's see what we've got now. Okay? Now, this time we did introduce a u. I'm not absolutely certain it's necessary. But this form here that we have, what would be your trig substitution? But it helped to go back a few slides. Ha! Here it is. That one has a minus. This one has a minus. The only one with a plus is the tangent substitution. So we're going to let, remember our u was 2x equal a was 1 tangent theta. So 2x is equal to tan theta. Does that make sense? Got it? Yay or nay? Okay? So let's go back where we were. There we go. All right, so we are going to let not x now, but 2x, that's your u, is equal to a, which is 1, tangent theta. Okay? Then give me the then. Okay? You don't want to give me a then. Then, now, we could do this if you wanted to. Divide both sides by 2. Okay with that? Okay. So that would give you x equal tan theta, 1/2 tan theta. How about that? It's pretty simple. So if this is then what you got, what's your next step? We don't have a x by itself here, but we have a dx. So what is dx? If x equal 1/2 tangent theta, what is dx? I'll do the first part, so 1/2. What's the derivative of tangent? Secant squared. Okay, remembered. Secant squared theta. And then we have one little other thing to write. If you have a d on this side, you d theta. Perfect. All right, so that takes care of my dx. Now let's take care of the radical down there. If 2x is equal to tan theta, 4x squared is the square of that. So 4x squared is equal to tangent squared theta, right? Square 2x, you get 4x squared. Tangent theta, you get tangent squared theta, right? Now, so what's under the radical here is 4x squared plus 1. So that would be tangent squared theta plus 1, right? You just added 1 to both sides. Now we've got what's under the radical, okay? What is tangent squared theta plus 1? Now you have your trig functions squared. Something, light bulbs should start flashing in your brain to what to investigate. Pythagorean identities. Is that one of our Pythagorean identities? I gotta talk with some trig instructors here. Okay, let's do this. What is the main, the easy, the one we all know and love, Pythagorean identity? Do you say sine squared theta plus cosine squared theta is equal to 1, right? Now if we're going to get a tangent out of that, what is tangent in regard to sines and cosines? Sine over cosine. So let's divide this by cosine squared theta, divide this by cosine squared theta, divide this by cosine squared theta. Okay? What sine over cosine is? You just told me. Sine over cosine is tangent. So this is tangent squared theta plus, and what's cosine over cosine? 1 plus 1 is equal to, 1 is 1 over cosine. Second? 1 over cosine. No, 1 over cosine can't be 1. Cosine's a function. Another trig identity. It's just not Pythagorean, it's what they call a reciprocal identity. 1 over cosine is? Second? Sine, you said? No, what did you say?
That's what I said.
No, it's not, because cosine squared, cosines and sines are related by what we just did, sine squared minus cosine. Cosine squared is equal to 1 minus sine squared, so that wouldn't be working here. What's your secant? You're absolutely right. So this will be secant squared theta, right? So tangent squared theta plus 1, which is what this is, and what that is, that's going to be secant theta. So what we have so far, our integral, the dx here, I'm going to put the 1/2 on the outside, and we'll put a secant squared theta d theta here, because that's the dx part, right? Divided by the square root of secant squared theta. Well, what's the square root of secant squared? Secant, yes, exactly. That's secant theta. All right, well, this secant theta will go into that. Secant squared theta, secant theta times, right? So now we have simply the integral, 1/2 the integral of secant theta d theta. That looks pretty simple. The trouble is it's not particularly easy to do. Unless you look in the table or something. Because we did this in the last chapter. I'm sorry, I keep saying chapter. Section. The trigonometric identity, integration by, no, I've turned too far. Trigonometric integrals, okay? If you look back on page, goodness gracious, what's that? Something about my book. All right. I know it's in here because we did it, but I can't see it. Well, I thought we did it. It does show up on page 535, not in the form I was looking for it, but when the integral is of the form integral of secant m theta dx, the secant m x dx, where m is odd and positive, it is here, it's odd and it's 1, use integration by parts, okay? That's not really the best way to go. Okay. I can't remember where it is we did this, but I know we did. Maybe it was in last term. But none of you have your books anyway. But if you go to the front inside cover of your book where your derivatives and integrals are, the integral of secant u du, which is exactly what we're dealing with here, is this weird one that's the log of absolute value secant u plus tangent u plus c. So go to your table. If you can't get anything else to work, go to the table. So this will be 1/2 the log of absolute value secant theta plus tangent theta plus c. Okay. But again, we didn't start with thetas. We started with x's. So we got to figure out what these are. And you remember how we did that? Go back to this, our original thing here. Tangent theta is equal to 2x. Now, I'm going to put something in here, tell me if it bothers you. Over 1. No, that doesn't bother us at all, does it? Now you draw your little picture with a right angle in it and make this be the angle theta, and you tell me what is 2x and what is 1. What is tangent theta in terms of your some old hens? Is the definition for tangent theta? Came pretty close to saying it in the last problem. Tangent is, in terms of opposites, adjacents, and hypotenuses. What is tangent? Folks, you need to know your trig. What is it? What's tangent? Yes, opposite over adjacent. So this, the opposite here must be 2x, and the adjacent must be 1. Okay? Now, if that's the case, we need to figure out what secant theta is. Anyone remember what secant theta is?
Would it be the opposite of it?
No. You mean the reciprocal of it? No, that would be cotangent. What is secant? Second? 1 over cosine. And what is cosine? Adjacent over hypotenuse. So secant would then be hypotenuse over adjacent. We got to figure out what hypotenuse is. And what's that? That's pretty easy. Square root of the sum of the squares of the other two sides. Right? Pythagorean theorem, c squared is a squared plus b squared. So that would be 4x squared plus 1, right? Which is exactly what we see here. Okay? So secant theta would be hypotenuse over adjacent, which is just the square root of 4x squared plus 1. Now we need to figure out what tangent is. What is tangent theta? Is what? 2x what? Yeah, you're absolutely right. Just 2x. You're right. 2x over 1 is what I was looking for, but you don't need to write it that way. All right, I think we got it now, folks. Can I erase my scratch work here because I don't have room to keep it? Okay? Oh! No, I'll write it back. I'll write it back. Wait. Tangent theta. I think that was it. Yep. All right, everybody got it? All right, now can I erase it? Okay. We'll get rid of that and that and that. Whoa! I hope y'all have it written down because it just erased what I wanted to keep. Okay? So this integral is equal to 1/2 the natural log of, what was secant theta? Someone wrote it. Please tell me you wrote it. It was square root of 4x squared plus 1. Okay? Plus tangent theta, and what was it? 2x. All right. Now, if we keep x's always positive, then there's no way this could be a negative number, so I'm going to lose the absolute value sign. Okay? I'll just put parentheses in its place. Okay? Plus c. Okay. They kept the absolute values in their place. Okay? And I'm not really sure why.
Probably just like to guarantee no error.
What's that?
I said probably just to like guarantee no error, like just in case it was another problem.
Right. Perhaps so. Well, the doing of this one, we were just always assuming we were with in positive x's. So I guess you could say without that assumption, you might need it. So we'll leave it there. Okay. Now, they have a little sentence here before we go to example 3 that when we have our form here, any of these forms, like a squared minus u squared, okay, we were doing the square root of that, but what they're going to have us now is using an exponential form of n over 2. Now, if that was a square root, that'd be 1 over 2, okay? But if it's n over 2, that's just simply the square root of, that's what the 2 tells you, is the square root of a squared minus u squared raised to the nth power. Or you could have made the argument down here raised to the nth power. One or the other. It doesn't matter which. Usually better to put the n on the outside there. And the reason they mentioned this is that's what we're going to do next. Okay? We'll proceed with that. So I'm going, if it's okay, going on and erasing this. Any problem? Okay. So let's go to example 3. Now this example 3, by the way, it says see larsoncalculus.com for an interactive version of this type of example. So you can go from there. I'm sorry. I did manage to eat all my lunch, but I didn't get to drink very much. Now my head's clogging up again. It does it when I don't get enough fluid. So sorry. We'll try to continue. So here's our integral. Good old dx up there by itself. And then we have an x squared plus 1. And that's raised to the 3/2 power in the denominator. Okay? Now, if you were doing a substitution, which you can't, if there was a 2x up there, substitution all the way, okay, then I would definitely leave this in exponential notation. I like dealing with it, integrating exponents rather than radicals. However, this isn't that way. So they actually recommend going back to the radical, okay? And I kind of hate to do it, but it is, in these kind of problems, that probably is the easiest way for you to see them. Because you see, when we think Pythagorean theorem, we always have a radical there. Square root of c squared minus a squared, or whatever. It's always a square root. It's not to the 1/2 power. So we're going to go backwards on this and make that in radical notation. So let's take this denominator, x squared plus 1 to the 3/2 power. And how do I write that in radical notation? There are actually 2 ways. Anyone know? Second? Okay, how do I write that in a radical form rather than exponential form? Okay, did I hear a square root? Okay. X squared plus 1. Cube it. Okay, you can either cube it here or you can cube it there. One or the other, but not both, obviously. Now, I think it's better to put the cube on the outside. So we have that radical by itself with no cubes on it. So that, I think, is how we're going to proceed, at least for now. We're not going to do that one. We'll have the cube on the outside. You okay with it? Both of those are legitimate. You can either cube on the outside or cube on the inside. I think it'll be easier on us if we cube on the inside. Because you see, we're used to that kind of form, aren't we? Okay? So we'll keep the cube on the outside. Okay. And it is true both ways. Both ways are fine. All right. Now, what kind of form is this? What might be our substitution here? When you have the plus, which do you use? Okay, we use tangent. So we'll say let, and here, remember with the trig substitutions, you always use the variable they gave you to be the one you're substituting. So this is going to be like x equal what? Said tangent, so I know there's going to be a tangent in there. And usually our favorite angle variable is theta, okay? And what's going to be, is this got a coefficient? It's just 1, because that's a 1 there. So that's it right there. There's our substitution. Okay? If that's our substitution, now we go back and see if we can reproduce any of the forms here. So I'm going to rewrite this as the integral of dx over the square root of x squared plus 1 cubed. Okay? So if x is tangent theta, there's 3 things we got to do with that. What are they? What's one of them? It's ground we plowed before, so what are they? Second? Yes, find dx. Okay? Then dx is equal to what? Dx, what's the derivative of a tangent? Secant squared theta. With what else? D theta. Don't forget to put a d's with d's. Okay? Now the other thing, that accounts for the dx here, or here. Okay? Now we got to get our x squared. So if x is tangent theta, then x squared is equal to what? Tangent squared theta. Okay. Then x squared plus 1 is equal to tangent squared theta plus 1. Just add 1 to both of those. And then we want the square root of that. The square root of x squared plus 1 is equal to the square root of tangent squared theta plus 1. Well, what is tangent squared theta plus 1? Anybody? Tangent squared theta plus 1. We already had a time or two today, I think. Tangent squared theta plus 1. Pythagorean identity. Oh, how soon we forget. We worked it out, beginning with sine squared plus cosine equal 1. It's what? Secant squared, you're absolutely right. So this is equal to the square root of secant squared theta. Because tangent squared theta plus 1 is secant squared theta. But what is the square root of secant squared? Secant theta. All right. Now I think we have everything we need. Let's go back and do our integration. The integral of, and your dx is secant squared theta d theta from right up here. Divided by, and down here we have this whole thing in the parentheses here, the square root of x squared plus 1. That's equal to secant theta. But that is cubed, right? So that means that would be secant cubed theta. Well, the secant squared will go into secant 2 cubed 1 over secant. So that's what this is. I can't write. Okay. Man. Ugh. Ugh. I feel like my head is just completely clogging up. What is 1 over secant? Oh boy. Second?
I didn't hear you.
What is 1 over secant? That thing right there. 1 over secant. Gotta talk with your trig teachers. I know who yours was. And yours, I think. Think yours too? No,
Mine from year, like so many years ago.
Huh?
Like more than.
Were you not in my class? Oh, okay. You were, right? I know who yours was. Okay. Okay. What is 1 over secant? Cosine, exactly. That's the reciprocal identity. And I think this has turned out pretty easy. This will be the integral of cosine theta d theta. And what is the antiderivative of cosine? Is sine theta. You're absolutely right. Sine theta plus what? C. Okay. Now, we're still in terms of thetas here. We need to get back in terms of x's. So we go back up here to x is equal to tangent theta. Okay, the very top line there, x equal tangent theta. Now, let's do my little triangle here. That's my right angle there. Let this be my angle theta. And we're doing tangent theta is what? That is one ugly right triangle, isn't it? Okay. Don't comment. Okay. Let's see if I can clean it up just a little bit. That's a little bit better, maybe. What is, if that's our triangle and tangent theta is equal to x, what is tangent theta in terms of old hens?
X squared plus 1.
It's what?
X squared plus 1. What is it?
Okay. Does this help to put it over 1? Say that again. Okay, so x is the opposite and 1 is the adjacent. Right? Opposite over adjacent. That's tangent. So I've drawn it right. So what's the hypotenuse over here? The square root of x squared plus 1, which is exactly what we've got here. Right? That's why radical forms are okay here. So what is sine? If tangent theta is x over 1, what is sine theta? It's what? It's opposite over hypotenuse, which is x over the square root of x squared plus 1. Let's see. All right, I think that's it. Let's see how the book did. X over the square root of x squared plus 1 plus c. We got it. Make sense? Got it? Any questions?
I just need to this refresh.
What's that?
I said, no, I just got to refresh.
Okay. All right, they also skipped example 4, so you ready for it? Yay or nay? All right. We have to, is that what you said? All right, I hear the enthusiasm there. All right, here's one. And this one, they really are going to do something a little different. The integral of, from the square root of 3 to 2. We've got limits, okay? Of, this time the radical's in the numerator. Oh my goodness, can we do this? X squared minus 3 divided by x. And then we're going to have a dx. All right. What would be your approach here? Now, if those were reversed, the x on top and the square root of x squared plus minus 3 in the bottom, substitution! We don't have to do any of this trig stuff. You'll just do a straight substitution. But with them reversed like that, they aren't going to work. Okay? So what do we try next? Anybody? Use which? Okay. Sine would be if it was 3 minus x squared. So this is x squared minus 3. Okay. We usually don't use the cos. So just lose the co and what do you have? No, we just said we don't use sine. Sine would be 3 minus x squared. And you said cosecant, didn't you? Oh, cosine. Okay, sorry.
Yeah, you said lose the cos.
Okay, I'm sorry. I thought you said cosecant. That's what you should have said. Okay, no. And then I said lose the co, and what would you have? Secant. Yeah, the secant is the u squared minus a squared, right? Say yes. Okay, all right, good. Yeah, it's the one. Yeah. So it's going to be a secant substitution. Okay, so it's going to be let x equal, now, this is a little different in yet another way. Okay, remember before, all of our constants have been perfect squares up till now. That one's not. Can we still do this? Well, what did we do to those perfect squares? Like 9, what do? Use a yeah. You would have used a 3. If it had been a 4, you'd have used a 2. When it was a 1, we used a 1. When it's a 3, we use a, what do we do to 9 to get 3? Take a square root. From 4 to get 2, take a square root. 1 to get 1, take a square root. 3 to get? Square root of 3, you got it. So the x here will be the square root of 3, and what trig function do we say? Secant theta. All right. Like pulling teeth, okay? Now, what's our next step? One of the next steps, I don't care which way you go. Anybody? Anybody at all? What do we always do once we've figured out what the substitution variable is? Then do the dx. Then dx is equal to, anyone remember that one? Square root of 3, I got that part. Derivative of secant. This is sort of a strange one. Secant theta tangent theta. That's a weird one, remember? Okay. What else are we going to need to do to it? Going to need to square it, aren't we? Yay or nay? Yeah. Yay. Okay. So x squared would be 3 secant squared, right? That's pretty easy. And when you subtract 3 from that, minus 3, x squared minus 3, which is what we have in there, that will be x squared minus 3 will be 3 times secant squared theta minus 1. right? Oh, you let me get away with this. Left off my d theta there, didn't I? Y'all were going to tell me that, weren't you? Yeah, right. Okay. Okay. All right. Well, what's secant squared theta minus 1? Pythagorean identity. No. Lose the code. Tangent squared. Okay. Right? Because we had tangent squared plus 1 and secant squared. Subtract 1 from both sides. You got tangent squared is equal to secant squared minus 1. Right? So this will be 3 times tangent squared theta. Okay? Now, but we have that under a radical, so the square root of that, of x squared minus 3, will be the square root of 3 times tangent theta. Right? All right.
Isn't that square root anymore? Oh, okay.
No, we took a square root. Yeah. Okay. All right. So let's see what we got. We got the integral of root 3 to 2. Now, I may want to change these later. Hang on to those thoughts. I think I do want to change them. I'm going to leave them blank for now. Okay? All right. Your square root of x squared minus 3 is, I'm going to put the root 3 out front, tangent theta, and my dx is another root 3, so that's just going to be a 3 out front, secant theta, times another tangent theta, which is going to be a d tangent squared theta, d theta. Okay? That looks a little squirrely, so let me take that off. Okay, literally looks squirrely. Divided by, and what was our x? The x was a root 3. Well, that takes us back to a root 3 again, right? I probably should have left them all in there. Secant theta. Well, that's good. The secant thetas go away, right? So we're left with that integral. Root 3 times the integral of tangent squared theta d theta. Let me make sure I haven't done something stupid here. Nope, that's exactly right. Kinda. Oh, I'm on the wrong page. Yeah. Okay. Now, what we haven't done here is put our limits in. And since we changed from x's to theta, see, this is when x equals this and x equals that. But we changed the thetas here, so we need to get what thetas are. So we go up to here. When x is equal to, which one you want to start with, the upper or lower, I don't care. Which you want to use. Okay. When x is root 3, so put a root 3 in for x, and then you have root 3 is equal to root 3 secant theta. What would theta be? Well, divide both sides by root 3, and you get 1 is equal to secant theta. What would theta be for secant? Secant theta is equal to 1. What angle theta must you have? 2 pi, you said? Okay. I'm thinking if that will work. I think it will, but also that's the same as 0, isn't it? Yeah. Because the, because secant is 1 over cosine. Cosine is 1 at 0, so 2 pi is correct too, but let's just keep it close to the origin, so 0. So then this one will be a 0. Theta will be a 0 when x equal 2 pi. When x equal 2, then you have 2 over root 3 is equal to secant theta. So secant theta is equal to 2 over root 3. I just divided both sides by root 3. What angle would that be for theta? Isn't this the same as saying that cosine theta is equal to root 3 over 2? Because those are reciprocals, right? And what angle theta has a cosine of root 3 over 2? Pi over 6. Yes, absolutely right. So this one up here is pi 6. All right. So those are our limits for theta. All right. Now, so let me write those in. 0 to pi 6. All right. Now, we have a root 3 here. Tangent theta is not a antiderivative. It's not a derivative of anything, okay, that I know of. But remember, secant theta is. And since 0 to pi 6, tangent theta is, from right up here, secant squared theta minus 1. Remember when we did that? That's what tangent squared is, right? So I know how to do the integral of secant squared. What would that be? Antiderivative of secant squared is? Oh, how long ago? Tangent. That's your tangent theta. And then you just have a minus 1. Antiderivative of theta is theta. D theta is theta. So this would be root 3 times tangent theta, evaluated from 0 to pi 6, minus theta. Antiderivative 1 d theta is theta, and that's evaluated from 0 to pi 6. Now, I could have put them together, but I thought I wanted to separate them, okay? So it doesn't matter which way you do it, I just thought it would be better. So this will be a root 3. Now, what's the tangent of pi 6? Does anyone recall? Tangent of pi 6. Does anyone know what sine of pi 6 is? 1/2. Cosine of pi 6? Square root of 3 over 2. So this would be 1 over root 3, wouldn't it? Right? So this would be 1 over root 3. And what's the tangent of 0? 0. So we have 1 over root 3 times 1 over root 3 times 1 over root 3 minus, and this is just going to be pi 6. So I don't need these extra brackets in here, so I'm going to take them out. And what will this be then? Sort of bizarre, but it's true. 1 minus root 3/6 over times pi. Strange answer. Hopefully it's true. Well, they wrote it slightly differently, but the same thing. 1 minus the square root of 3 pi over 6. 1 minus square root of 3 pi over 6. And you can pull out your calculator and see what that is. It's a pretty small number. Okay? Oh, me. Now, they drew their little triangle, but they really never used it much, did they? I don't think they did. And there's no reason to convert back to x like they do at the bottom of the page, so I don't even see why do that. Okay. Now, they're talking about something here that I mentioned before, but let me reiterate it again. Picture this now, folks. 2 is the square root of 4, right? And this is the square root of 3. So basically, you're talking about a pretty small range in x. Square root of 3 is 1.7, and that's 2. So it's a really small interval of x. The important thing is it doesn't include any place where any of our functions are not defined. In other words, you're basically all in the first quadrant, okay? Because everything here is in pretty good shape. What you couldn't have is look at it this way, 0 to pi 6, all in the first quadrant. Now think about your secants and tangents. That's what we're using mostly here, right? Secant and tangent are defined between minus pi halves and pi halves. Everything here is in between that. So we're in good shape. If we had had something from outside here to inside there, couldn't do it. I mean, you might have come up with an answer, but it would make no sense because you can't move across the discontinuity. You have to integrate within a region that you're defined. You're not defined at minus pi halves. So your interval could not jump over minus pi halves. Between 0 and pi 6, yeah. You're all within the secant, you're all within the tangent. Yeah, they're all good there. But you couldn't go pi 6 to 5 pi 6, right? Because then you would jump across the pi halves. Can't do it. You cannot do that. That's what the bottom part of the page and most of the next page is talking about. All right. With that done, let's move on to, and they show you an example. You could have done it from minus 2 to minus root 3. That would have been okay because that would have been over here in this part. But you couldn't cross it. Okay. So trigonometric substitution, can be used to find 3 integrals listed in the next section, next theorem. These integrals will be encountered several times, they promise. Okay. Special integration formulas when a is greater than 0, some positive number. So here we have the integral of square root of a squared minus u squared. You tell me, what are you going to be using to do that? Which one? Which substitution? That's going to be your sign substitution, okay? Now, they give you this, we'll actually do it in a minute. Which one will you use here? Now, cosine. You could have used cosine there, but sine or cosine there, what do you use here? We just did it. That's the secant one. Okay? Now, you don't see a secant over here. The reason you don't, But you do see a log, and remember the antiderivative of log is secant plus tangent, and that's what you got here. If that was secant, this will be tangent. Okay, so, and this one, what would be your substitution there? That's your tangent substitution. And you see the same type of form here. Now, why are they just giving them to you and not having you derive them? I'm not really sure. Okay. Exercise 65 is to derive these, to verify them. And those are the substitutions you would use. So I guess for now we're not going to do them, okay, unless you want to see one or more than one of them done. But what they're suggesting now, get to know them, not memorize them. Recognize them, and then when they do come up, then go to the table or to this theorem or wherever and just write down the answer, rather than having to redo it every time. Okay, now, any of you want to see that done, to see how they came up with this? I'll be glad to do that, but you can just use these. That's what they're saying. Use them if you need them. So what you want? Want to see one done or not? It's up to you. Just use them when you need them? Okay. All right. So I think we're ready for the next applications. All right. Find the arc length of the graph of f of x is equal to 1/2 x squared. That's this parabola down here, from x equals 0 to x equals 1, as shown in the figure. We want the length of that arc down there. Okay? Now, they show the input when x equals 0, of course this is 0. When x is equal to 1, this will be 1/2. So here is the arc length we're talking about, between 0, 0, and 1, 1/2. Okay. Now, the question is, do you remember your arc length formula? Have we done an arc length formula? I think we have. Yeah. They at least act like they have. You remember that? Yeah or no? Yeah. Okay. So let's do it. Remember the several steps in the arc length formula. And basically this. First thing you do is take a derivative. What's f prime of x? There's your f of x. What's the derivative of that? I need to talk to your Cal 1 instructor. It's what? What's the derivative of it? F of x is 1/2 x squared. What's f prime? What's the derivative of f? Come on, please. This is a little discouraging here. Remember how to do a derivative? X. You're absolutely right. 2 times 1/2 is 1, and you drop the the exponent by 1. It's just x. What's that?
It doesn't count that I said 1x.
I can't hear.
It doesn't count that I said 1x.
Oh, I didn't hear it. Okay, please speak loud so I can hear it. Yeah, x is fine. Okay. 1x is fine. Okay. The next thing you do with the arc length formula is square that derivative. So what's the square of that? F prime of x squared would then be, second, x squared. Perfect. Okay. Now, the next thing you do with it, I don't know if you remember this, you add 1 to it. Okay? So 1 plus f prime of x squared is equal to 1 plus x squared. And then the final thing you do with it is take the square root of it. Okay? So then you take the square root of this, which will be the square root of that. Right? Now here's your formula for arc length, if you remember. S is equal to the integral, and you're doing along x's, so it'll be 0 to 1 of this thing right here, the square root of 1 plus f prime squared of x dx. So that'd be 1 plus x squared dx. Okay. Now, I don't know if you remember how we did that, but it was, if you remember, it was taking little sections of this and assuming they're straight lines, and then those straight lines would be the hypotenuse of dx and dy, and dx is just 1, and dy dx is that, and you take the square root of 1 plus the y prime, you know, and that's what you're doing, summing all those up. So, there's the arc length. Okay? How do we calculate that? It's a lot like something we've done, doesn't it? Tangent substitution, exactly. So our substitution is let, but remember we let the variable be the substitute. X equal what? You said it. Tangent theta. Then, and what are the thens we use? Dx equal, say again, secant squared theta, d theta, don't forget your d theta. Also another then is x squared equal tangent squared, right? And 1 plus x squared equal 1 plus tangent squared. And that, by the way, is equal to secant squared, right? 1 plus tangent squared, secant squared theta. And then the square root of this will be the square root of that, which is the square root of this. So that would be the square root of 1 plus x squared is equal to secant theta secant theta. Okay. Now. All right. So now we plug. Here's the interval we're doing. So S is equal to the interval from 0 to 1, integral from 0 to 1. And this is just simply secant theta times dx is secant squared theta, so that will give us secant cubed theta d theta, right? Now, does anyone remember how we did that kind of interval? Remember this. This one isn't. Okay. This is one, and we said it earlier today, and rather than going through the gory details of it, remember back, and I reference you back to 8.2, and I found this very one for you. On page 535, the integral in the form of secant m dx, where m is odd and positive. Exactly what we've got here. Okay? it says use integration by parts as illustrated in example 5 of 8.2. Okay? So integration by parts. Yeah, okay. So S is equal to the integral from 0 to 1. Now we need to do integration by parts. Now remember the parts, we let one be a U and the other be a dV. Okay? And the dV part is always going to have the d theta with it. The d's go together. Okay. Now, what we're going to do is split this into secant and secant squared. Now, if you remember, secant squared is the derivative of tangent, right? Remember that? So therefore, let secant squared be the dV, because it is the derivative, right? Yeah, it's the derivative of tangent. So that means the u is just going to be the secant part. It's a little backwards from what we usually did, but it works. So let u equal secant theta, and dV equal secant squared, I can't write, secant squared theta. Okay. How are we doing on time, by the way? We're supposed to go until 2:15? I think we've already passed it, haven't we? Sorry about that. In fact, I think we're supposed to go till 2:10.
Yeah.
All right, sorry about that. We're going to have to do this one next time. But I've got you started. You should be able to do it. So I'm going to make the mark here. Y'all should have stopped me. But let's not reinvent the whole wheel, but let's start from there. And this will be homework exercises, then do either 3 or 5. They're both at calcchat.com. Do either 9 or 7 or 9. They're both at CalcChat. 7's at CalcView. Do either 11 or 13. They're both at CalcChat. 15 or 17, both at CalcChat. 19, any of the odds 19 to 31, they're all at CalcChat. 19's at CalcView. Either 33 or 35, they're both at CalcChat. 35's at CalcView. Any of the odds 37 to 41, they're all at CalcChat. 37's at CalcView. You can look at, explore 43 or 45 if you'd like. There's true false 47 and 49. You could do those if you'd like, and we'll hold off on the application until next time. Good deal. Y'all should have stopped me sooner.
I thought we had time then.
I did
It's
too.
only lasts like an hour and 40 minutes.
Yeah.
And it has an hour and 38 right there.
Yeah, well, we didn't get started right at 2. Yeah, remember, I was a little late getting in. Okay.